Is this online? Let me see. I'm trying a new way of making these videos. Excuse me while I check. That's not working. So complicated. Oh, that says that's working there. Oh, is it actually coming now? Oh, is someone there? Is someone actually there? Oh my gosh. Where is this? So strange. It says it's broadcasting, but I just don't actually believe it. Oh, that's live. Oh, that's actually me. Hey, this is live. I so apologise. So apologise if there we go. Aha. Great. I didn't expect to be on here so soon, but you know how these things are when you do something and then suddenly everything kind of falls together in place. Not that I've solved, obviously it's just really seriously difficult, but there's some structure has fallen out of it, which is that, you know, there's some pretty well-defined problems now, and they're more computer science-y really than anything else, I would say. And that, all right, we started off with the Aharonov weak model, and then saw we had this problem with trying to correlate near field and far field, and here near field and far field. So then we made contact with Langlands and found this lovely extremal parallelogram that supports the Yang-Mills in this bizarre form. I'm just scribbling what I saw of Langland's pictures of showing a double cover in this thing, and I can only assume that this is corresponding to the SU part and this is corresponding to the SU3 part. Now, and this must somehow correspond, because again, I'm not an algebraicist, but I can just, things jump out at me sometimes. I see things like as a geometer, and GF27 just carries everything we need just so perfectly. Obviously there are other Galois fields too, and they will be probably very useful for representing space-time coordinates. But when we're using charges, we'll be wanting to use GF27. Because the thing is, we have to construct the space-time coordinates as well, because this is a completely This is a completely emergent theory where we're building it up from literally nothing. There was a talk that I gave, but I deleted it because it went wrong. But now I wish I hadn't deleted it because it led to all of this. It made a mistake. The thing was that I thought I could just do an inner product here, so I'm kind of backtracking over stuff that got missed. And I'm also, I think the other thing that got missed was the notion, the Einsteinian notion of quantum mechanics. And this is very important because the Einsteinian notion of quantum mechanics is it should all be based on quantum number. So it's essentially, he's essentially saying it's a number theoretical thing, not necessarily, that's why. And so what I'm trying to do here is formulate that, make some kind of sense about it, and obviously, as everyone knows by now, if anyone's been following, we're trying to collapse the multiverse without using Born's rule. So we've set ourselves, you know, a harsh constraint here, but it looks actually almost doable, and I think I found a way of doing it. I mean, it's so beautiful. It literally, like an artist, beautiful. It actually look, when you visualize it and you start to see what's going on, it's just like, that's all I can say. And so that's to recap. So there's all this strange stuff going on here, and we're trying to make sense of it. And, you know, we've got some kind of Penrose stuff going on in the background, and I just wanted to, you know, take my hat off, not that I got a hat on, to Roger, because really I think I underestimated his cosmology, because I think the thing was that I couldn't see how late time could correspond to early time. I just couldn't see that. But this is a cyclic cosmology, but it's not quite the same cyclic cosmology, but we do get echoes of the last universe, but it's much more blatant, and it really is going to take a lot of explaining for someone to say why this isn't the case. Circles in the sky, unfortunately, were just statistically likely whatever model you used, but this isn't. This is like, I just looked up a paper on it and I was reading through it and I was going, I'll try and get the paper that it was, but it just, everything tallied. And so we've got these elliptical equations, so we're flattening them out using the phi naught to mu mapping that we still haven't pinned down, but I think it's just a double cover, and where we're using an inversion here basically, because mu has to always be less than 1, and this is a complex number. And if you think about an elliptical field, we have definitely got a double cover involved because we've got the two orientations of the ellipse. Maybe I can draw this. So I mean, it should be pretty obvious, but yeah, there's a double cover involved here, and that's explicit because this thing is just a complex number, and this thing is less than 1. So we got to map this thing onto that, and the only way we're going to be able to do that is with a 1 over z. And so we've got a inside to outside mapping, and hence I've written UV equals 1 over IR. They are exactly the same dynamics via the fact that we have to map phi naught to mu using a 1 over z. Okay, and then obviously everything just runs into PGL 2, C, and you can actually start writing out using this technique where the initial conditions are going to be, because they're going to be like the smallest initial conditions that you can possibly code. So, because we've all got to generate this up from number theory, so it's not like you've got the whole of the real numbers. You've got like measure zero sets of it, and as Noel proved when we studied these things in detail, he actually proved that it is measure zero, but as I'm saying that using beautiful proof that was published, and I mean I wasn't sure whether I was going to talk about the one that was the one that I said that he could solve, and there was another one that he couldn't solve, but I thought I did, but it certainly wasn't published, even though, because it was completely incomprehensible. And the other thing, because it was just pure geometry like this and it was looking at something, because there's a peculiar symmetry that comes out of this that has no obvious algebraic reasoning, but when you look at it geometrically, it's like, and you follow the mappings, you begin to go, okay, that's going to go there, and that's going to go there, and that's going to cycle over there, and we're going to slowly fill out this kind of modular thing. I'll get some fractals of it. The other thing is I did all of this 30 years ago, so I've lost a lot of the source code. And that it was basically a large chunk of my PhD was on this stuff. And I was basically after finding pretty pictures and trying to understand enough about the formulas so that I could get a good computer simulation, an accurate rendering of conformal mappings, and some of them being transcendental functions was very, very difficult. So I kind of worked out various different distortion bounds techniques using the Kobe distortion techniques. And that gave me some kind of handle on being able to plot these, as Noel would say, wretched prime ends, because that was the other unfortunate thing that I didn't talk about. We've got some nice stuff going on, because if we're dealing with algebraic surfaces, we've only got prime ends of the first type, and so we can forget about the really pathological cases when boundary behavior gets really messed up. So and at the moment it is very much a discrete theory. I can't even see whether, I mean, yeah, you could imagine taking limits of this, and then you could imagine somehow some larger transcendental theory. Well, there has to be, really, but again, it's another thunk to kind of get up to what it is, or thunks beyond thunks, because, you know, as I wrote here, we're at a very low level of the arithmetical hierarchy here. Whatever level I'm working at with my meta thinking here, it's still nowhere near enough to crack anything like the Riemann hypothesis, even though it actually gives quite a little bit of insight, because the entire technique is absolutely applicable to the psi function, which is just like, whoa, what are lifting the boundary conditions, and what's the propagate, you know, it's like, whoa. And so then that makes contact with the Hilbert program as well, but it's like, so it's got another bit of it. It's like, and so that's kind of bringing down the Langlands to the actual number theory side, because I got completely lost in the zeta function for many, many years, and it was a rabbit hole with rabbit holes of rabbit holes. And a lot of these techniques that I'm using now actually came out of that, particularly the Riemann surface stuff, because the Riemann surfaces for the zeta function are transcendental, so dealing with algebraic surfaces is like a bit of relief, really. And but you've got all these mysterious things in string theory, like the regularization, the famous one that I've just kind of scribbled a few things on here, that, you know, the infamous equals -1/12, which is so key in the string theory revolution, you know. We really, I would like to get a better handle on this, because that whole regularization thing seems to me to be lurking, something seems to be lurking there. That for me, that's not, I know there are better ways of doing it, but I want to know more about that. Because this is talking about the transcendental theory to me, you see, because if we think about it, all of this is talking about the number theory side of it, but this is saying something about the transcendental side of it in the limit. And that's like, you know, and this is where it runs into things like the Church-Turing thesis, because if you believe the Church-Turing thesis, there is nothing beyond this. But if something is beyond the Church-Turing thesis, and surely we just say that that is just another thunk, and I always think there is something beyond the Church-Turing thesis, because I come from the transcendental school, so I'm a transcendentalist. And I don't think everything is just natural numbers. I don't think it's enough. I just think we're living at a low level of vibration where we can only communicate in symbols. And so I can't explain to you what I can convey and what I've seen about these geometries. I have to try and kind of convey what I've seen in terms of symbolism, which gets totally into what Turing is talking about in you know, the halting problem, because this is a matter when you're defining a Turing machine. But you see, Turing is defining his Turing machines in terms of logic, but we're kind of going way, way lower than that, because we're trying to derive this thing from essentially from the lambda calculus. And that's a much, much harder job to do, because you've got no concept of data or anything like that. You just start with a function of the notion of recursion. Not even, you know, it just starts so low. You know, you've got to start with the doubly named CCC, the closed Cartesian category, and just build up from there, and keep on breaking out of these firewalls using the tunnels. And so the firewall theorem isn't wrong. Physics totally changes when you cross an event horizon. This is what I'm going to show. Now, what we have to understand first is this amazing property of GF27. It's got so many amazing properties. I mean, I kind of found this when I was going insane on Sabine's site. Because what happened is, all right, I found the tunnels, this tunneling technique, and it totally, I was like crossing black hole boundaries using it, and it was driving me a bit barking, to be honest. And then I kind of went absolutely wild, blogging or just ranting on Sabine's site. And but some real stuff fell out of it, particularly noticing that I couldn't keep, some particles had to like fly off into sectors, and there had to be other dimensions of time and compact time, and it was like, it was driving me crazy. I couldn't make head nor tail of it. But then the theories kind of settled down, and once you could totally compactify time, and so since we're working with gravity, everything has to be a loop. And that was the name of the original theory that I sent along, was called superloop theory, not superstring theory, and it was actually a quasi-superloop theory. So it's a quasi, yeah, that's it. The loops come first and then trees come second in this theory. So we're always taking square roots, so we're always getting Riemann surface with branch points and cuts. But we're always dealing with quadratic cuts, and that's the beauty of it. So it's always yes-no decisions. So essentially, yeah, everything as we've seen in the early, I don't know whether I recorded when we went down to the Planck scale, and we saw everything was just a classical bit using holography. But so now we've kind of seen, now we can actually see what these bits are doing, because they're part of the thunk. It's so sneaky. There's a computer you know, this is just what you love seeing as a computer program, because it's like, I broke through that firewall like this. This is how to get through a firewall. You know, it's hacker's skill. Give me a firewall, I'll get the data out of it. Okay, so this is how you tunnel through a firewall, right down to the Planck level. And why? All right, why are we doing this? Well, the thing is, in the deleted episode, I was going, blah, 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 and we go round and round this loop, and we interact with ourselves, and then we get to the time, and then all we need to do is do this. We basically need to, you know, take, it's not actually this, but we need to do something like this. We need to take something, yeah, we need to take something with actually its supersymmetric partner, which I suppose we can get via the FFT. So, yeah, it's all symmetry. So this has to, oh, that is neat, actually. This happens in real time to me, because this is a little mistake. It's a little, it's a little oversimplified, but it actually shows something, because it's a simpler problem. And sometimes in maths, as everyone knows, it's easier to tackle a simpler problem than a harder problem. But now, so this simple problem is, this is like the tunneled inner product. So this is how you get around the Born rule. We want to know the inner product without making we want to make as weak as possible observation of So what are we going to do? First of all, we've got to collect all of the information that is going to, you can imagine you've got all of these particles interacting, and somehow we're going to have to get that information somewhere to process it. And when you're writing an algorithm, there are two stages to the algorithm, basically. Data collection, when you're drawing all the data into a point and you've massaged it into the right form that you need to actually do the final computation with. And then you do your final computation, and then you have to unwind everything backwards. Now, that's a normal stack-based model, but we're having to use a tunneling model here. And it's exactly the same fundamentally once you get the algebras right. But remember, we're taking square roots of functions. All right, so this is the thing. All right, so what we're doing is just in the same way that we got functions. That's a top-level function. It's like a loop. It's taking you up somewhere and then it's taking you down. But we need to cut that. We need to cut that function just like we cut a string. And so in programming, the way that you cut that function is you cut it in half and it turns into two coroutines. So basically we can map, in computer terms, coroutines to strings, and we can map loops to functions. So now we've got a nice duality there that we can start working with. And we've also got these nice dualities between strings representing entanglements between points. Because now that we've got, two spaces with essentially the strings just in being the entanglement between these spaces, and rather than dealing with one great 10-dimensional space, trying to get a 4-dimensional space, and then find the right manifold that fits in a conform. We can only work in some conformal gauge, and we can't do any of this shifting around with heat. So the thing was, the problem with the normal phrasing of it was there too many degrees of freedom in the Einstein metric. So what this does is we've essentially pulled the metric back onto the world sheet, into these grains of rice, which are encoding the elliptical, complex dilatations, and this is exactly what's going on here. So let's go on to, right, so Einstein's QM is that the whole thing should be driven off number theory, and that what you're trying to do is you're trying to get around this, the whole notion is this equation here, which is exactly what Langland's was about. And what this means is, what I've done is I've put some question marks here, because if you're a programmer, you would really want to make everything dependent on G. Because these are, again, we've got a Hamiltonian here, but you're a programmer, you want to set that Hamiltonian. And if you're the great spirit, you certainly want to set that Hamiltonian. So I think we can almost take these question marks off. And if we take the question marks off, then we give ourselves a much more relevant problem. Because then we're saying your trajectory through this space depends on who you are. And that to some extent makes sense, because that's the way the world is. If you've got a high security pass, you can get through the security door, but if you don't, you don't. And so by making these things have a component of the Gödel number in them, then, and I'd say let's take now I'm talking through it. You see, I think in real time, I can't think like most people do. I have to do it in real time. So we take off these question marks because I make mistakes. That's the thing. So now once we've got everything a function of the Gödel number, then we truly can make a proper programmable system, because, and that means that we have this kind of power too, and we're kind of showing it in quantum computing, because we can set Hamiltonians, we can set this V function, we can potentially even start to set this V to N, this N parameter here. So we have to assume that this is basically it, and that this is the number theoretical foundation of quantum field theory. And then, of course, once everything is and notice here I'm only using one quantum number, G, because that's a Gödel quantum number. So remember, all your Gödel theory, we need multiplicative number theory, and we're wrapping up a whole load of Gödel fields and Gödel number fields, and we have a function neg, which takes us to the negative, which is, of course, we're just going to get Gödel's proof. You can see that it's just coming into, we've got binary things, so we're going to get Gödel's proof out of this generating eternal universes. And so you can see these are all virtual particles. That's the point, because they've all got a finite lifetime. So we can say, right, we've got this virtual particle that's sending information from A to B, and then it just disappears. And we're setting, but using the supersymmetry, we can be saying, all right, we want this to happen here, but we're not having, you see, the Fock space was interfering in the configuration space was interfering in the bulk. But that's why we want to pull all of the stuff into the boundary conditions of the singularity. Because if you have anything in the bulk, well, first of all, it's not the bulk anymore. So, I mean, it's like, ugh. Right, so we Gödelize it, and then everyone knows their Gödel's theorem. We just make it eat itself, eat its own tail, and negate itself, and just crash the system, and give us eternal universes and whole families of them. But you would imagine that we would land up with like the first one that it runs into. Although in the multiverse, of course, there will be lots, but this does kind of run into that notion of an evolutionary universe. That if at the really top of it, it's just like Beverken counting through every hypothesis and every proof, you know, Erdosh's book, until the first thing that what's the first thing that stump Erdosh's book is it's the maximum complexity of the algorithms. But then what you can do is you can, even if you're close to that point, yeah. You can say, okay, well, let's create another axiomatic system and have a thunk between it. So this is the thing, you can thunk between different realities using, and they can be different mathematical realities, as long as you've got a way in and a way to tunnel back the information back out in a consistent manner, and obviously in a relatively consistent manner, then you're all right. So what are these mysterious bits doing? Well, we're up in this world here, okay, in the SU2, in the electroweak world. And as we've seen, it's like weak force first. I mean, it's like crazy, isn't it? And then weak force equals weak observation. I mean, there's some degree of entanglement of names going on here. And that wasn't me, I promise. And so there, right, we've got this little dipole with one little thing up and one little thing down. So the electron has come along here, and here's the event horizon. Oh, this event horizon, by the way, is a nucleus. Or any SU3 charge has to be, because remember, think about it. We're not dealing with numbers that are SU2 cross SU1. No, they're SU2 cross U1 in the GF27 representation. We got to squeeze a U1 out of that GF representation, so we're going to have to use 2 extra gluons for that. So that's going to give us 6 quarks, you know, instead of 8. So it's not like, oh, you got the photon and then you got these funny extra 2 8-fold gates. No. Why do people think you'd like steal what the complex dilatation field? I don't know, but you just get these literally unused fields in GF27 that you can reuse for this U1. And so basically then you're just trying to carry information in and out. So this is the electroweak world. And then you need to get some information, say, down into the nucleus where the inner product's going to be performed. Right? This is what we're going to try and do. We're going to try and perform A with the FFT of A. Well, it's actually a really supersymmetric FFA, you know, with no peaking. No peaking unless it's in a black hole at the Planck horizon level. So we have got to get, because it's got to take account of everything. It's a local interaction, but so we have to do that process somewhere. So what we're going to do is we're going to be doing it right at the bottom of the gravitational well, and that's the other thing. Why, if you remember the last episode, it was that lovely, beautifully symmetric equation plus UV and IR weird, you know, UV equals 1 over IR expressions. And we can really see that now, UV equals 1R, because what is going on here? Because remember, we're just trying to do the FFT, which is getting a rainbow. And we get rainbows in our world. You know, we see these beautiful, beautiful rainbows. And these rainbows manifest all the way down, because basically what's happening is a rainbow is the fast Fourier transform. I'm talking about fast Fourier transform because I can't really talk about the Fourier transform here if we're doing a discrete operation. And there probably is an absolutely beautiful form of the FFT in GF27 involving GF7 coefficients as well, or it has to actually interact with whatever the real representation is. So there's probably some beautiful modular way of doing all of this arithmetic that is just like, and you know, it's one for the use string theory lot to decode that, or if it just falls through a black hole somewhere into my skull, then I'll try and do another blog about it. All right, so tunneling. The code's on the net. I gave you the link. There's an easy, not easy. I'll try and get the algebra together. It's all written, so I can show it works. It's really lovely as well. Well, it's just the square root of functions, and it shows you it's the algebra of them. And it just is. It is this. So you've got to make it a function sometime, but you're kind of deferring everything and eliding every call to a jump. So it's really sneaky, and at the same time, tunneling through all of the protocols and stuff like that you've got to do. So this is to show you how to tunnel through into SU3. All right. So we've got to, there's something happens here because we've got to get some information out here. All right, we can think about this like actually we got to be very careful here. Let's think about this as an analogy at the moment, because that's what it is. Problem with me is this, I can't really get started. If I find a mistake, I will just like because but what I'm talking about a basic idea here rather than an actual working bit of code. It's a principle. It's a like. But I know that most of this idea works because I've tested it already. It's just a case of working out what these details are. And as we know, if everything is depending on everything else, these actions can be extraordinarily difficult. But what we're doing again, you see, is we're removing all the degrees of freedom. So this is all of Einstein's QM in a nutshell. Is every quantum degree of freedom. Supersymmetry, everything, the lot becomes a quantum number, and that is the whole principle of this. And that neg becomes, so the quantum negation is a Gödelizable operation. So, all right, we want to get stuff in and out of the Planck level. So we're at this level. We've got to get information in, right, because the Planck level, remember, is the level where we're going to be hiding the actual inner product, because all of the information has to be, let me see whether I can draw on this, because that's going to make it much easier. All the information has to be flowing in like this, like leaving a little thing there to like get back, and every time, so it's gained a little bit of mass here, and it's, so say this is an electron, and then it's become, when it's interacting in the nucleus, it's become, well, I just call it E2. I don't know all these names. I think it's what's called, what do you call it? Is it a muon? Yeah, it's a muon and then a tau. And so the tau is the form of the electron that is interacting at the Planck level. But sometimes these things seem to shoot out at us. I mean, we do see them decay, but what that might be is it's just, then, so what we're doing is we're doing our important computations down here. Again, so this is our final black hole layer, and again, this is the interesting thing that asymptotic safety has been saying there's nothing below the Planck level, and this would agree with that. So it's nice to have something that like tallies with something as powerful as asymptotic safety, because I think asymptotic safety and asymptotic freedom are two of those things that if you break them, it's a showstopper. And like for what was the thing? I think axionic like Alps are like not good in asymptotic safety terms, and people have got very convoluted arguments for how to do that kind of thing. But I think that's why we should be looking more at the bizarre effects that things like quantized gravity cause, such as your quantized gravity, quantized acceleration, literally, because of the holographic. That's actually comes from the holographic principle, but I haven't really got fully into that. Just to do with the quantization of surface area. Because remember, surface area is the thing that we have to go with. I'm not interested in quantizing length, that's irrelevant. And particularly if we're using this kind of system here, it's not like we have to add, we can make things quite small very easily, and then we can be doing this UV equals IR stuff, and then the whole kind of thing is you land up with these really lovely kind of continued fraction patterns where I'll try and draw it actually. This is the one that I found when I was at Warwick, and so there's this whole great big zone where it's not ergodic. Everything's in a 3 cycle, and then it goes down like this. Let's see whether I can remember this. I haven't drawn this for years and years and years. And you've got to work out which regions are black. I don't think I can do that quite yet, but I can show you the basic ideas. And then it's doing, when you've drawn this thing enough, you begin to see why it actually lands up being symmetric. So the thing is that the limit set in the limit is not symmetric when you do it. Like each iteration is not symmetric, but the symmetry emerges. So I mean, who knows? I'd always wondered whether there was some link to this, but maybe mainly because I never found, although I found a geometric proof of the fact that this had this axis of symmetry here in for the limit set. So this is just taking, well, it was named after me, this fraction. So, and there's the Hurwitz is the other case. So this is this complex, and the actual, the remainder, that it contains, we've got these bits here which are in the limit sets, and the rest of it, if you look at the rest of it, it's actually got Lebesgue measure 0, and that was what Knoll proved. And but so what I'm saying is we've got, actually, if you look at it from the number theoretical point, that we don't have much choice for where to put stuff, initial positions. And I'd always thought that when you do this on the quaternions, it just starts looking like galaxies and stuff like that. So, and if you add in some distortions, and this is a Euclidean view of it, you know, you add in a space-time view of it, and you're actually getting a pretty good image or a possibility of where things are, but just taking the point of a transcendentalist rather than being, you know, someone who's going to be able to prove rigorously that that are the kind of initial conditions that are going to have this extremely low entropy. But I guess that is the kind of principle of the evolutionary universe. All right, and so the other thing that is important was that we found that we needed all these clocks, like 3 clocks. So we got different clocks. We got a really, really high speed one down here, and then we got a kind of slower one, and then we got well, is it no, what is it? Oh, I mean, it's, oh gosh, it's this thing here, isn't it? No, these clock frequencies, you know, these are like femtoseconds and stuff like that. And then there's another scale that things are happening even quicker at. And so at this level, so this is handy. So we've got these different layers of clocks. So, but there's some level of mixing. So because remember, these clock signals are dimensions, and these dimensions do start interacting with the particles here. And so that shows up as an Unruh-like effect, where the particles actually start morphing into other particles. I mean, it's so cute. And, right, so clock mixing to Unruh. And so that kind of like, and that makes, so that it gives us our relativity, and that mixes in very, very nicely with holography. But I could talk about this for hours and hours and hours, because, all right, so the other thing is the FFT is, you know, is a rainbow effect. So we've got our light coming in like that, and then we got it splitting into a rainbow like this. So we got our different frequencies like that. But because this is a non-linear medium, we can be kind of like routing things off in all kinds of wonderful directions, down to and other things can be coming in, because other calculations need to be finding roots, and electrons can find, you know, nothing needs, the other thing is in the bulk, nothing needs to be obeying the laws of relativity. This is the region where relativity can be broken. So nothing needs to be following geodesics. Everything can be following its own little chemical potentials, essentially, and deviating off, and right, that one's going that, maybe wiggling around a bit, delaying in another place, interacting with something else, and then finally going down there. And then once all the computations are done, it's all got to unwind like that. And so this is the way that we can technically do this kind of no peaking. And there is a little bit of peaking. Okay, you're doing some peaking because you are having an energy effect, but it's not actually having an effect, a side effect on anything else other than the gravitational effect. And that's very important, because the thing about functional programming is side effect free. So what you've done is you've represented state in a manner that is side effect free. And this is very, very important, that you can't do this kind of work without these kind of computer programming techniques. There is no way of doing it unless you use them. And this is what computer programmers have found. This is what, I guess, why I've done it so many years. I went from, you know, doing maths to, I don't know why I did it, but this is obviously it. And now I'm in Roger. What's this episode called? Which way are we pointing? Well, you know, James Webb, I didn't quite get it. I had a feeling that people were never going to see baby universes. Because you see, the thing is this whole system is in equilibrium. So we can't really have... oh yeah, that's the thing. So we've got this system. What's so neat about it is that it doesn't really do anything until it's in equilibrium, as far as I can tell. Or if it does, it's just like chaos. It really is chaos. Multiple mixing of multiple universes and multiple realities, half existing and half weakly existing. It's just like what in spiritual terms would be called the astral plane. And as someone who the it's probably good to get into the shamanistic creation myths here, because this is what the shamanists would call chaos. Before the equilibrium state set in, it was chaos, and we might be some way away from it and have some element of chaos. Eventually, it should settle into an equilibrium. But if it's not an equilibrium, and things never are, then the story then is that the Great Spirit made a hoop pass not to keep out the chaos. I'm drawing a very bad hoop pass not there. Now, as soon as I saw the hoop pass not, I thought, that's a conformal mapping. And so you've got, immediately we've got this structure emerging. And now there's directionality here in the count. So 0, 1, this is 1, 2, 3, 4. Now, I haven't fully decoded this yet, but it seems to be the idea is that this is the full meaning of the 4 direction. Well, not the full meaning, gosh, there's so many meanings to this. This is your map. This is where the best place to be is most of the time, and if you're going to journey out to one of these states, you get your return journey. So it teaches you to do these string closed loops. And that's the other thing. In shamanism, everything is cyclical. Progress is just a part of a cycle, if you mean it. It's just everything gets reversed. But actually, this is quite interesting. Well, if it's algebraic, yeah, that's true. Everything is a cycle, and there is no transcendental layer. But I do think there's something more. And who knows what it is, such a, creature limited by symbols. So you got 1, 2, 3, 4, and then there are 4 resonances. 4. So this is 5, and then so you go up to 20. So you get 4 resonances of this, and then you go back down to 0 again. So that's, and the other thing is that the ultimate, if there is an ultimate revelation, it's got a name, it's called The Great Alone. And it's one of the most, it's like the end and the beginning is the Great Alone. And the idea is we are all alone. Every atom in us is alone. Every electron in us, or every string or whatever, is alone and is trying desperately to relate with something else. And so this is happening at every level. We start with something that's alone, trying to find something. It's like saying, is there anyone out there? Is there anyone? Yes, yeah. I think I went through this, having the conversation with the self to try and create a weak reality. And so, where are we? Well, I propose a modification of Penrose's CCC. Which is that we are roughly here. Between, because I was confused, because all of this reasoning tended to suggest that all these event horizons should be 2-dimensional. But if the CMB is 3-dimensional, that's a bit kind of like, all right, it could be a 3-brain, I suppose. I mean, I'm not saying it's not. Who knows? But I just had another idea, and which is that actually we've got two brains. So there's our forward CMB here, which is we're heading towards, and this will be blue, yeah. And then we'll have our red CMB here. And now the red CMB is going to have these, when we're looking back through the singularity, which is acting as a Planck scale pinhole telescope, essentially, because everything is going through this, we've actually get a really good view of the previous universe, supersymmetric universe. And what we can see is it looks really, really, really different. It's like these weird red galaxies and cartwheel, I mean, there are those amazing kind of cartwheel galaxies that seem to have like a massive great wormhole in the middle. And the other thing is that obviously, you know, when you get your black hole like that, you're going to get all of these magnetic fields because it can't eat the magnetic fields. So you're going to get all of these magnetics, and this thing is going to be spinning near the speed of light. So you're going to get all sorts of effects, but without any charge. Just you know, someone has to tell me what it means for it just to have weak hypercharge and isospin. I don't understand fully what that means. I just know that that's, in this case, is what happens. But someone out there will be able to point us in the right direction, because I haven't got a clue what it means. But what I do mean, things have to leave a little walnut, a couple of walnuts on every horizon. Every horizon looks the same. It's just like here it's black and white. Here is 3 colours, so it's really, really colourful. You can imagine all the rainbows going on here, and oh my word, once I manage to get some pictures of what's down here, it's going to look quite stunning. Because I say that, this is what my PhD was about. It was like how to get pictures of this stuff with Mobius transforms. This is where I lived. Inside equals outside, UV equals IR, and Kobe distortion theorems and stuff like that. But and there's a mistake in my PhD right near the end that doesn't help, because I think, oh God, I need my PhD again, and so I was going to drag it out. And I know that the main formula in there has got like something that's a wrong way around in there, and I'm like going, oh, this is in the end of the PhD. I'm kind of going, this is strange. I don't know why that looks like that. I can't understand. And I go, oh my God, it's this bug in the code. I tried to correct it actually, but it was like 10 years after I found it. After I found the bug, like 10 years later. Oh, and this is the other thing, is you know, private communications. All of these communications, yeah. If look, the analogy of a firewall is really, really good, because if we've got all of this security, that means if I'm sending a message from A to B, no one else can read it. We don't want any other particle to like be snooping on it. And that is, so what this is doing, this whole thing is wrapping stuff into black holes. Nothing can take it. There's no peaking until you get to the Planck scale, basically. So that's kind of it. You're allowed to peak at the Planck scale, and then everything else is just busing, as it's called in computer parlance. It's data in, data out. But the computing is actually happening at the Planck scale, and gravity is the thing that is basically rooting stuff down. And all of the other forces, which are all the same particles all together, remember, to split up in different ways with square roots. And so that's the beauty of it. Again, I can't see exactly how that's done, but it has to be said, it's pretty gorgeous. Right, so we've got a Planck scale telescope, which is actually amazingly giving us, if this is the case, I mean, I could be completely barking up the wrong tree here, but if it is, then we're seeing this weird red universe, which is the supersymmetric universe, and then we're seeing this blue universe, which is our future. And the important thing is, and this is what, Roger was here, these two sides are different. Not just color-wise. If you analyze them, their parities are different. Yeah, so they don't match statistically, and in ways that are peculiar. And I think I might have mentioned this. I might be wittering on, but basically, I think this is the way to do CCC. I think the cold red universe was the momentum space of our last universe, and I guess that's so clever. So look at this. So you see, this is like the next universe is over there. So we are getting this gorgeous kind of effect where who knows? I mean, essentially, information could actually be, being sent right the way forwards and backwards this way. So, and in shamanism it said, that reincarnation is a theorem. And this almost looks like that, because it shows that we might think that we are mortal beings, but actually we're this eternal golden braid that is weaving through these. So in the next universe, I'll probably be female, and then you see we alternate. So it's like female, male. And I was born with this knowledge, you see. This is a peculiar thing, and I've been putting it back together in reverse. So I've always had a very clear view of this and of where we're going. So I guess I'm pretty well close to wrapping this up, and enjoy your ride is all I can say, because it's a pretty beautiful one, and maybe I'll try and do some journeys down to the Planck scale. That looks really, 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 really fun. What on earth is going on down there? I mean, well, we know it's computing, but we know basically, well, where is it? This is the thing. Where is the Beltrami? Is it needing to solve the Beltrami equation? Or is it, no, the Beltrami equation is what's, again, it's this kind of thing, because we got to something, either, the Beltrami solution is kind of emergent. That's the thing, because this Beltrami, it also has, maybe, or is this the truly transcendental component? I don't know. There's some beautiful stuff going on down at this, what the shamans call the pixel plane. And I just recommend that that I've gone down this path for the fact that I didn't want beliefs. I didn't want to feel that I was I want to feel like my thoughts are flexible, that I can go, yeah, that might be the case, maybe that isn't, because if I believe something, then there's always someone who doesn't believe it, and it's kind of, I just find it, it's always suited me, but that I think I'm unusual in that way. I don't think most people are like that. But anyway, I think now it's so late at night, and I think, I've tried to convey what I think is Einstein's QM, how we can get infinite universes out of it. The potential, this is a fantastic way of doing encryption, wrapping stuff up in tunnels, essentially, and that is what we're doing. But I guess the thing is, so this is what I was saying, if you're doing it the number theoretical way, you have to be, I think, I say you have to be, the natural way to do this tunneling in a public universe would be to use encryption and encryption keys. And then yeah, I think that's the way to secure this very, very open protocol otherwise. And isn't that bizarre? What is this emergent encryption? Well, I suppose it's fast scrambling, isn't it? You know, fast scrambling, fast Fourier transform is pretty well the same thing. Ergodic systems, there are plenty of number theoretical systems that show ergodicity, plenty that show non-ergodicity. So, you know, we seem to have a very versatile system where we can, you know, thunk between the different, we can thunk between the different string models. You know, hey, it might even be possible to go into different Kahler manifolds and things like that, and different Calabi-Yau spaces. I don't know. Anything's possible. So, I think, as a programmer, I look at this, I call it API, and I say this is a very flexible API, and I couldn't see a lot of things you couldn't do with it. But I think let's wrap it up for there. I need some sleep, but I think, you know, I think Roger nailed it, and that's really why I'm doing this post, because it all came out like really suddenly as I was packing up, and I was thinking, oh, but yeah, I and having the idea that the CMB is actually a Planck level microscope is like, well, it kind of means that, and this whole UV equals IR, it's much easier to observe the IR than it is to do the UV. So we can, this is a sen, oh gosh! I think you can see it, can't you? It's much easier to observe the IR. So if UV equals 1 over IR, you don't waste energy. You just send it low energy and do 1 over, and then you get high energy version of it. Anyway, I think that just about wraps it up before the next burst of nonsense comes through. Alright, I hope you've all enjoyed it, and hopefully I won't be back within the next hour or two. So enjoy. All the best. Bye.